Now let's look at the data set that was collected. So the data set is about total of about 13 million users collected ran from August to October 2011, a total of 13 million users. It's almost close to the entire Foursquare in terms of the number of users that are using it. And the total data set contains 10 million tips. So what we are interested in the data, particularly the questions that we're asking, as I said, we're interested in mostly the tips, dons, and mayorships, right? Because that's the information that is publicly available. What can you use this information for in terms of actually getting the location of the particular user? So the total number of tips that are available in the data set is about 10 million. Total number of dons is about 9 million. And the mayorship is about 15 million. And different venues that are available are about 15 million again. So let's just look at just characterization of this data, which is what kind of generally about the data set that is available. So we look at every table and every figure in this paper. So here if you look at the number in the data set is 13 million UHC. UHC stands for user home city. VL stands for venue location. The number of venues that are available, and DI stands for geographic information. Right, of course, there's going to be some information, some locations which are not going to be valid, right? For example, something in the middle of a sea, you're not going to get any location, and there are locations that may be generated, which is somebody's heart, right? HEART. And so these kind of locations has to be removed. That's what happened between number in the data set and valid GI. Valid but ambiguous, which is it is valid, but we are not able to figure out the exact location. Reverse lookup and find out the location. That falls into the third row. Non-geographic information and empty entries. So essentially the data set was pruned to get data which the researchers can actually use to do the analysis, right? This is what even you would do for the homeworks that you did. You collected some data, but you probably did not do the way to actually prune the data to get more accurate, more specific data, right? So the quality of geographic information is continent, country, state, and these information that are available in this data set is number of users, number of venues. Country, state, county, city, neighborhood, area of interest or airport, street, point of interest, and coordinates. So all these pieces of information you will get in your JSON when you collect data from Foursquare. And this was basically pruned to get more quality data which can be used for analysis. Is that making sense? So these are called exploratory data analysis. Here we're just explaining the data itself, describing the data in terms of what is available in the data that was collected. Multiple tools were used, so let me just show you one of them, which is developer.yahoo.com/geo/placefinder. These kind of tools lets you to actually reverse look up a place and find out where they are in the map. If you give them location, it can actually give you the latitude, longitude, even the other way around. You give the latitude, longitude, it will give you the location. Many of such tools were used in this particular research to find out the location of the check-ins, location of tips and other information that was collected. So if you look at the rest of the analysis, so here is the two figures that we'll also talk about. First, let's talk about the figure 1, which is shown on the left, but let's look at the content of the figure 1. Shown in figure 1 and consistent with previous analysis of Foursquare, the distribution of number of mayorships, tips and dons. So this is what you would do first when you collect such data. So one of the things that you would have generally seen in social media analysis is to show whether the data is a power law, or show whether the data that you've collected from social media follows the Pareto Principle, which is to say that 20% of the users only actually contribute to the 80% of the content that is generated on social media, right? One of the similar type of graph was drawn here, which is to see the distribution of mayorship tips and done per users, and the inference is that they're skewed with a heavy tail, implying that few users have many mayorships, tips or dons, while vast majority of them have only one mayorship, tip or don. So that's essentially what a Pareto principle is. That's essentially what a power law is also. So if you look at the graph which is on the left for the figure 1, you will see the same thing, which is large amount of users actually have a small amount of users have, so that's what is here. So let's take, if it were 90% of the data is getting generated by small set of users, majority of the users who are here don't contribute to any of the mayorships, tips or dons. Right, so that's the graph that you would read. Similarly, let's go to figure 2. Figure 2 shows the distribution of number of mayorships, tips and dons per city, considering only cities with at least one instance of the attribute. So essentially you wanted to see whether from a city, whether you're able to get a lot of mayorship, tips and dons. This can actually help find out how the data is. As shown, the distributions are also very skewed, with few cities having as many as 100 mayorship, tips or dons. Right. So again, if you look at figure 2, the distribution is very similar in terms of the small number of cities having large number of mayorship, tips and dons, and a large number of cities don't have these. So these are all large. So if you look at it, somewhere around 80, 90 or something, there's only small set of cities here. Large amount of cities don't have mayorship, tips and dons, or has very little mayorship, tips and dons, because the condition was that they were considering only cities with at least one instance of the attribute, which is they should have had one tip, mayorship or don. So then looking at correlation between the number of mayorship, tips and dons per city, they found that high correlation between the number of mayorship and the number of tips across cities with a coefficient of 0.78. Similarly, the correlation is also high between number of mayorships and the number of dons, which is if you're a high mayor, If there are more mayorships there in a city, there's a high chance that there will be more of tips and dons also. This is helping us to understand that, okay, if I find cities which have a high mayorship, I should be able to find there should be more of tips and dons also there. So if you look at the tips are concentrated in different locations around the earth, which is, if you remember, tips of the content that people post for a particular venue. The top 3 cities in the number tips are New York, Jakarta, and Sao Paulo, with a total of 600,000 tips. Dons, on the other hand, tend to be concentrated in venues in the US, in cities like, of course, New York, Chicago, and San Francisco. In total, they have about 1 million dons. So, which is to show that some cities, some popular cities, have a lot of these tips and dons. New York being common in both tips and dons. That's again to say that cities generate a lot of these tips, mayorships, and dons, and of course this would also probably lead into check-ins also. So here is another graph which we will see, figure 3 and figure 3. Before that we'll see so figure 3 shows these distributions in maps of the globe, with each point representing a city with venues with at least one mayorship, tip, and don. So essentially, until now we only saw per city what is happening. Now when you look at it in the map, the figure 3 actually shows the results. As the map shows, Foursquare venues are spread all over the world, including remote places such as Svalbard and Archipelago in the Arctic Ocean. So for example, let's go look at the figure 3A, B, and C. So if this is the mayorship, this is basically showing you every dot in this graph, every blue dot in this graph, figure 3A shows you the distribution of the mayorships that are available around the world, that were done around the world. Figure 3B shows you the tips that were done. So if you see, earlier we saw that there is a high correlation between mayorship, tips, and dons. Therefore, when mayorships are high, there's going to be tips and dons also which are high. So you can clearly see heavy concentration on many places in the world. And the last one is the dons. The figure 3C shows you every green dot is a don from that particular location. So this basically shows you mayorships, the blue dot tips, the red dot, and the green dot being dons. So that's figure 3. Is denser with the total number of unique cities. So the distribution of mayorships shown in figure 3A is denser with the total number of unique cities being 79,000. So 79,000 cities have check-ins, have mayorships in the figure 3A in the total data. And if you look at the figure 3B, somewhat sparser tip map for figure 3B indicates that there are many cities, particularly in Canada, Australia, and Central Asia and Africa, where despite the existence of venues and mayors, users do not post tips. So therefore, there is a chance that there are mayorships in that location, but not tips. Figure 3C reveals an even sparser map with most activity concentrated in touristic or developed areas such as USA, Western Europe, and South Asia. So essentially, even though there is a correlation between mayorships, tips, and dons, there is actually some places which are sparser for tips and don'ts. So now let's look at figure 4. Figure 4 here, so this is figure 4. Figure 4 is showing you the cumulative distribution of time interval between consecutive tips and don'ts posted per user. Why is this interesting? This is interesting to find out about the activity or the frequency of activity of the users. This is figure 4. Figure 4 shows the cumulative distributions of these 4 meshes. We note that the distribution of minimum interactivity times is very skewed towards short periods of times, with almost 50% of the users posting consecutive tips and don'ts 1 hour apart. Right? So that just shows that there's a lot of content that are generated, a lot of tips are generated by users, tips and don'ts are generated by users within apart 1 hour. However, on average, median and maximum users do tend to experience very long periods of times between consecutive tips and don'ts. So essentially what this shows is, again, it's going back to the same power law concept. There are some set of users where the consecutive tips and don'ts are done very frequently, but there is a set of population where this distribution is actually pretty skewed, which is long time taken between 2 consecutive tips and don'ts. For instance, around 50% of the users have an average interactivity time of at least 450 hours. That's close to about 20 days, whereas around 80% of the users have a maximum interactivity of 167 hours, roughly a week. So here is the graph for cumulative distribution of time interval between consecutive tips and don'ts posted per user. It's the same thing as what we saw in the text. Now let's look at the next figure, figure 5. So this part we already saw. Figure 5 is basically looking at the same question, which is now we are analyzing the displacement between 2 venues. The last figure that we saw was looking at 2 different timing in which the post was done. Now we are looking at 2 different venues which is done by the same user consecutively. So let's look at the figure 5 first, and then I'll tell you what the figure 5 all means. So figure 5 is the cumulative distribution of displacement between consecutive tips and don'ts posted per user. So on the x-axis it is showing you the distance, on the y-axis it is showing you the number of the distribution. Figure 5 shows the distribution of these measures for all analyzed users. Around 36% of the users have average and maximum displacements of about 0 kilometers, right? Indicating very short distances within a few meters. 70% of the users have an average displacement of at most 150 kilometers, which is basically somebody moving between cities. And so I probably within Delhi, from Delhi, I go to Agra and then I do it check-in, or in Mathura, I do a check-in. Mathura, I do a tip or a done. That's what is actually captured here within 150 kilometers. And about 10% of the users have a maximum displacement of about 6,000 kilometers. This is probably international travel between two consecutive tips or downs. Right? So that shows what is the distribution of the users who we have in the data set, the consecutive consecutive tips or downs that they do on Foursquare. Let's go to the figure again. So this is basically showing you that 70% of the users are about 150 kilometers and the 10% is about the 7,000 kilometers. That's what you will see in this figure. So if you see here, 7,000 kilometers, so it's about the last 10% of the users who are about 7,000 kilometers. And then the very short is about 70%. Right? Average 70% is the green one is the average. The green square is the average. The red plus symbol is a median, triangle is a minimum, and the circle is the maximum. Right, so that gives you a sense of, so now what all we have seen? We have seen the time consecutive tips or downs, that is done with respect to time, consecutive tips or downs with respect to distance. Now we'll see the next figure. Next figure is actually a very interesting, next analysis is actually a very interesting analysis where they saw how frequently that the check-ins, the tips of the downs are coming back for that particular location, right? So this is distribution of the returning time, right? So, so if I check in, if I do a tip or a down in triple IT, how frequently do I actually do a tip or a down in that location? Right, figure 6 shows the distribution focusing on returning times under 360 hours, which account for 69.7% of all the measured observations. The curve shows clearly daily patterns with returning times, often being multiples of 24 hours, which is very similar to the distribution of returning times computed based on the check-in. So if you really look at it, what does it mean? Why is it 24 hours, right? Somebody checks into a office in the morning today, that they have got into the office, shop, institute and everything. They do the same check-in the next day. So that's what this means, right? Check-ins, the reference is given to another research where the check-ins were seen, but in this case we are also looking at the tips or the downs. That's a very interesting conclusion to know, or basically it's complementing the real world behavior that you could expect from the users. Here is the graph. If you see here, this is about 360 hours, and you can clearly see that it's coming back. So this is for every day: 24, 48, 72, 96, 120. So it's kind of coming back every 24 hours. And sometimes the frequency is also increasing if something happens. So this is 168 should be the week. So therefore there's a slight increase from the day that which is the 7th day of tips are done. I hope that's making sense. Essentially, the conclusion there is that people come back to that same location with the examples like me doing it in Triple IT Delhi. That's figure 6. That's an interesting analysis. So now what we'll do is, now we'll attack the question that we started off with, which is to find out how much can we actually infer about the user's home using this data. Right. So in this case, we are going to actually use data for most popular location among mayorships, tips, or dons of a user, a home location, using a majority voting scheme. So we're going to, I'm going to explain to you what this voting scheme is. There are two tables that we will look at, and we'll also see what the mechanisms the authors followed in terms of generating this information about what is the possible location that this person's home would be. Here is the scheme that they followed. They actually put the data into three buckets: class 0, class 1, and class 2. The class 0 is of the users who have single activity, either a mayorship, a tip, or a don. Right? They only have one activity in the data set. Whereas class 1 consists of users who have multiple activities with predominant location across them. So, for example, I have multiple tips or dons, mayorships in my account, but there's one which is very, very high, which is Triple IT Delhi for that matter. Class 2 is the consist of users with multiple activities in which there's no single location that stands out. So again, just to understand, if you understand this, I think the inferences become much simple. The logic the authors followed is that take all the users who have been doing this tips, dons, and mayorships in the data. Class 0 are the people who have only single activity, either a tip or a mayorship or a don. Class 1 is a set of people who are where there's one majority location that shows up for them. Class 2 is a set of people where multiple activities are done, but no single location is actually predominant in their activity. Right? So that's the kind of classification that they made with the users. Now I'll show you two tables. One is the number of people, number of the data points from this data set. If you just consider the class 0, class 1, and class 2, how many people are actually where you can infer home city, home state, and home country. So how do we read this graph? How do you read this table? This table is this column is showing you features, mayorships, tips are done, mayorship plus tip, mayorship plus done, tip plus done, and all of them. Right? So which is, if you take only the mayorship, what is the class 0? Which is only if I consider mayorship and there's only one activity by this user, there are about 727,000 data points in class 0. 847,000 where there are users where one location is actually predominant, and 239,000 there is no location that is predominant. That's how you read this table. Right? So if you look at mayorship, 727,000, mayorship plus tip, 898,000. So obviously mayorship plus tip will be higher, all will be higher of all of them, bigger than all of them. Right? That's for the city. For the state, so for the state, 700,000 is for class 0, 900,000 is for class 1, 100,000 is for class 2. Similarly for the country. Right? So that's giving you a sense of the data points or the pieces of information that is available for each of these features. Now let's look at accuracy, which is if I were to use this information and find out that mayorship, only using the mayorship, I'm able to find the home city 51.6% of percentage of the times. Well, wherever the percentage is higher, it's been actually kept in bold. So if you look at mayorship, it's class 0 and class 1. We can't do class 2 because it's actually the places where a particular location cannot be, one single location cannot be inferred. Which is the because our goal is to infer actually the home location. So if I have multiple location, I'm not going to use that column. That's why class 2 doesn't exist in accuracy. So which is 67% of the times home city can be inferred if I look at class 1 category of people, which is I do a lot of tips and dons, but my predominant place where I do a tip or a don is actually my home location. Right, home state becomes higher, 70%, and home country is even higher. Of course, the percentage for the country is going to be, so the percentage of city will always be lesser than state, will always be less than country, right? So because it's easier to get the country that I'm from India, more difficult to get that I'm from Tamil Nadu as a state. It's even more difficult to get that I'm from Chennai. That's about the inference of the home location. There's another interesting graph that authors have, which is figure 7, which let me show you the graph and then I'll try to explain it. So here figure 7 is cumulative distribution of distances between inferred and the declared home city, which is that because people actually declare that what the home location in these services also. If you go to my account, you will find that there is, if you go to my Facebook account, I probably say that I'm from, the current location is from New Delhi and my home location is from Chennai. So that information you can use to make the difference, which is what did we predict from the table that I showed you now, which is a prediction of my home location with class 0 or class 1, and then use it for finding the difference between what did I say and what I actually have. That's the graph here. So x-axis is the distance of inferred and the declared user home city, and y-axis is the probability. So this is how you will read the graph, which is distribution of these distances are shown in figure 7. We found that 46% of the distances are under 50 kilometers. That's what the authors did. They actually zoomed in. So this is, meaning this is 5,000 kilometers, whereas if you look at this graph, the inset graph is only for 100 kilometers. So you can clearly see that 46% of the distances are under 50 kilometers. So here is 50 kilometers, and if you see 46% should be somewhere here. Right? So 46% of the users are actually having the error between finding the home location and the actual location is about 50 kilometers. That's pretty small. If I was able to actually use this information with only 50 kilometers of error, which is actually just getting it from the general behavior tips and dons, that's quite effective. So if you just take this model and then if you look at it, the authors claim that 78% of the users within 50 kilometers of distance, which is what they're saying is combining these results with the correct inferences produced by our model, we find that we can correctly infer the city of around 78% of the users within 50 kilometers. Right? So whatever your city is, we'll be able to make an inference of that city of about 78% within the 50 kilometers of distance. So that gives you a sense of how. So if you remember, even in the abstract, I showed you the 78% of accuracy that the authors claim that you can find the home location. And of course, in the paper structure, you finish off with the conclusions and future work, and probably have some limitations if there's any data limitations in data methodology, any limitations in the paper. Right? So that gives you a sense of how a paper, meaning the things that you've seen in the class until now, which is to look at, take some data, do some analysis, make some inferences. How these inferences are put into a paper is what we saw in this particular lecture. And the focus was actually taking Foursquare and finding the home location. With that, I'll stop here for this paper, and I'll see you soon.